Let's talk about the signal-to-noise calculation. We offer a feature which automatically calculates the signal-to-noise, and I would like to spend some time explaining how that algorithm works. The algorithm cannot accomplish the same decisions as a trained analytical chemist, and that really boils down to picking the noise regions for the signal-to-noise calculations. And if that is required, the qualitative analysis feature has the ability for you to manually pick the noise regions, and that can be getting you the answer that a trained chemist can accomplish. Let's go to the definitions of the signal-to-noise. So I will go and look at the quantitation dataset help and search on noise and look at noise algorithm type. So here is the definition that I'd like to go through. If a chromatogram covers a retention time of 0 to 3 minutes, and there are two peaks, extending from 1.3 to 1.7 and 2.2 to 2.5, there will be 3 noise regions. One in the front of the peak, one in the middle of those 2 peaks, and one after the second peak. So one point to be made here, if there are multiple peaks integrated, the peak is not considered part of the noise. So here we get to the differentiation between the judgment that an analytical chemist may have of a peak actually being called noise. So below it goes further to talk about the different algorithms, the peak-to-peak, ASTM, and RMS, and I will leave that because those calculations are covered well in the literature. We are in batch at a glance. And let's look at the calibration samples only, levels 1 through 5, and look at the signal-to-noise, and you can see that it does jump around. So let me see if I can give you a visualization of why that happens. First, the calibration curve looks good, but I'll take that out of the way. Let's take a look at the peak that we've got here and the amount of noise that's associated with that particular peak. So this has a lower signal to noise, and that would mean that the noise has gotten significantly more than the signal. If I move to the next sample here, you'll see that here the signal has increased and the noise, relatively speaking, has decreased. So I get a larger signal to noise, and this does prove that if you divide a large number by a small number, a small variation in the small number will produce a dramatic difference. And that's what you're going to see here, and a reasonable explanation as to why the signal to noise does jump around. So I'd like to mention that folks have looked at calibration curves and expect this to be very linear in the signal to noise calculation. The expectations from the design were that the use of signal to noise would mainly be focused on looking for peaks that had a very low signal to noise and looking at the integration quality of those peaks. And the metric is very useful in that regard. An extreme case of the large number divided by a small number is illustrated here. If I look at the cocaine here, and this particular sample, cal level 2, I'll see that for the qualifier, I've got a signal to noise of infinity. Well, this is not totally uncommon, and there is a reason, and there does exist an explanation of why the noise, which we see here with the qualifier peak in blue, there is zero noise. Now, as I mentioned, there is an explanation of why zero noise occurs in MS-MS techniques, and the instrument design reasons why the triple produces such low noise. But I'll restrict myself here to the calculation. Well, if you're dividing by a very, very small number, then you are going to get a signal-to-noise calculation that is infinity. That's the math behind that calculation. That's the way it works. So I will leave you with the last thought of the use of the signal-to-noise, as I mentioned, for you to zero in on problem integration and the ability to get a quick view using the automatic calculation of how the signal-to-noise calculation happens in your batch. And I hope you find that feature useful. Otherwise, I will point to the fact that you can remove that column, and then you don't have to worry about seeing the signal-to-noise if that is a problem. Thank you for your attention.